Now, when you hear quantum, you might think of complex physics, something out of a science fiction movie. And you wouldn't be entirely wrong. But at its core, quantum computing is about harnessing the mind-bending laws of the quantum realm to solve problems that are simply impossible for even the most powerful supercomputers we have today. Think of it like this. A classical computer, the kind you use every day, stores information as bits, which are like light switches, either on or off. But a quantum computer uses qubits. These are more like dimmer switches, capable of being on, off, or somewhere in between. They can even be both on and off at the same time. This is thanks to a mind-blowing quantum phenomenon known as superposition. Why does this matter? Because this quantum weirdness allows quantum computers to explore a vast number of possibilities simultaneously. It's like searching a maze. A classical computer would try each path one by one. A quantum computer, it can explore all paths at once, and this is where Willow comes in. This isn't just another incremental step in computing. This is a leap. You see, for decades, one of the biggest hurdles in quantum computing has been errors. Qubits are incredibly fragile. Imagine trying to balance a pencil on its tip in a hurricane. The slightest disturbance and the whole thing collapses. But Google's team, led by the brilliant Hartmut Nevin, who, by the way, left the booming field of AI to pursue this very challenge, has achieved something remarkable with Willow. They've focused on quality over quantity. Instead of just cramming more qubits onto a chip, they've made them incredibly stable and accurate.
Willow is Google's newest and most powerful superconducting quantum computing chip, and the next step in our path towards building large-scale quantum computers and exploring their applications.
They've done this using a technique called exponential error correction. Imagine you're trying to send a message across a crowded, noisy room. You might repeat yourself several times, right? Willow does something similar. It uses multiple physical qubits to represent a single logical qubit, constantly checking and correcting for errors. And here's the kicker. They've achieved what's called below-threshold error correction. This means the more qubits they add, the lower the error rate gets. This is a monumental achievement. It's like finally figuring out how to not just balance that pencil in a hurricane, but to make it more stable the stronger the wind blows. Researchers have been working on this since 1995. That's almost 30 years of dedication, and Willow is one of the first to crack the code. This has enormous implications. It means we can now start building larger, more powerful quantum computers without them being crippled by errors. And that brings us to speed. To test Willow, Google used a benchmark called random circuit sampling. Think of it as an obstacle course designed to push quantum computers to their limits. So how did Willow do? It didn't just pass the test, it obliterated it. Willow completed this incredibly complex task in under 5 minutes. Now here's where it gets truly mind-blowing. A classical supercomputer, the most powerful ones we have, would take an estimated 10 septillion years to do the same. That's a 10 followed by 25 zeros. Longer than the universe has existed. I know it's hard to even fathom. We're talking about a completely different scale of computing power. It's like comparing a horse-drawn carriage to a spaceship. Now, Willow has 105 qubits. That might sound small compared to some other quantum processors out there. But remember, Google is focused on quality. It's like having a team of 105 highly trained special forces operatives versus a massive, untrained army. And this approach is paying off. Willow is setting new records in both error correction and speed, even with this relatively modest number of qubits. So what does this all mean? What can we do with this incredible power? Imagine designing entirely new materials, atom by atom. Imagine creating superconductors that work at room temperature, revolutionizing energy as we know it. Imagine simulating molecules with such precision that we can discover new drugs and personalized treatments, curing diseases that are currently incurable. Imagine creating AI so advanced that it can learn and adapt in ways we can only dream of today. Quantum computers could unlock new levels of AI, leading to breakthroughs in every field imaginable. And these are just a few examples. Quantum computing could revolutionize finance, allowing for more accurate market predictions. It could help us optimize traffic flow in our cities, making our daily commutes a breeze. It could even lead to more accurate weather forecasting, giving us more time to prepare for natural disasters. We're talking about a future where the impossible becomes possible. And Google isn't keeping this technology to themselves. They're making their software and educational resources open source, inviting researchers, developers, and curious minds from around the world to join them on this journey. This is a global effort to unlock a new era of discovery, and it's happening right now. We are at the dawn of the quantum age, and with breakthroughs like Willow, the future is not just bright, it's quantum bright. So I encourage you, stay curious, keep learning, and to be prepared to witness a revolution that will transform our world in ways we can only begin to imagine. The quantum future is here, and it's going to be extraordinary.
Benchmark. Willow hits a sweet spot across the full list. It has a large number of qubits with high connectivity and can run diverse applications. We measure low mean error rates across all operations with multiple native 2-qubit gates. We have greatly increased T1 times. We have very high measurement rates. And Willow is below the error correction threshold and performs random circuit sampling far beyond what is possible with classical computers. Looking to the future with Willow, we continue our journey towards building large-scale and useful error-corrected quantum computers that will push the boundaries of science and the exploration of nature.